Dr. White here, starting off section 1-2 on methods of enumeration. Warning, I've got my dog in the office with me. Bad idea. It seems to sense something outside in the hallway and is prone to bark every so often. Don't have time to go home and do it there. So let's just plow through. So methods of enumeration. Basically, it's counting sets of things, which sounds boring until you find that it's not. For example, consider the following problem. You're allowed to make a meal, and you've got these kind of limited choices. For your main course, you can choose one of these three things: a steak, beans, or macaroni and cheese. And for a beverage, you can choose one of these four things: water, Coke, or the more exciting beer and wine. Okay, four choices there. Stop, Demi. How many possible meals can you put together? Well, you could just sort of try to list them all out systematically. List the possibilities systematically. You can do so with a tree diagram if you like. You have like a starting point, that dot right there, okay? We haven't chosen anything yet. And let's say first you're going to choose your main course. And so you've got three choices represented by the three branches coming off of that dot. You've got a steak choice, you've got a bean choice, and you've got a macaroni and cheese choice, okay? And so that brings you to these three nodes, okay, where you've chosen your main course, but you still have to choose a beverage. And at each of those nodes, you have four choices for a beverage. You could do the water, you could do the Coke, you could do the beer or the wine, okay? And so if you follow out each of those nodes, just write out like the choices that you made along the way, then you've got your list of meals. You've got steak and water here, you've got steak and Coke here, and so on, all the way down. And if you count them up, that's 12 things, which is no surprise because you had three choices for your main course. And then no matter what choice you made for the main course, you had four choices for your beverage. 3 times 4 in the tree would make 12 little leaflets at the end of the tree. 12 possible meals. Okay? This gives rise to what we call the multiplication principle for enumerating. If you've got some kind of enumeration job, and you can find a way to break it down into tasks, then you can use some multiplication in order to figure out how many possible combinations of ways there are to do all the tasks together in sequence. So in this case, we had like a task 1 of choosing, the main course. And there were 4 ways to do that task. And then we had a task 2 of choosing the beverage, and there were 3 ways to perform task 1. Task 2, choosing the beverage, no matter how we chose to do task 1, there were going to be 4 ways to choose the beverage, and 4 times 3 made the number of ways to perform the sequence of tasks, okay? So that's the multiplication principle, and you can apply it even when there's more than 2 tasks. The only caution is that for each subsequent task, the number of ways you can do it has to be the same, no matter the choices that you've made for the previous tasks. Okay, that's the multiplication principle. Let's apply it here to the question of how many ways are there to take 4 people and put them in a row? So their order from left to right matters. Well, you can think of the job of putting them in as a row as broken down into a sequence of 4 tasks. Your first task, which I've got underneath the little line here, that's not division, it's just like a baseline. Underneath that line is the name of the task, pick the first person. And over it is the number of ways there are to perform that task. And since you haven't picked anybody yet, there's 4 ways. And then your second task is to pick the next person who's going to go to that person's left, I guess. And how many ways are there to do that? There's 3 ways. Notice it's not the same 3 people every time, right? Like if I've already picked George, he can't be one of the 3 people I'm going to pick next. But if I have not picked George, he could be one of the 3 next. The important thing is not the exact ways to perform task 2, it's that the number of ways stays the same no matter who I chose to go first. It's still a 3 no matter who I chose to go first. So I can use the multiplication principle. And then the next task is picking the 3rd person in the row. There are now only 2 ways to do that because I've already picked 2 people out of the 4. And by the time I get to my last task of picking the 4th person, I've only got 1 person left to pick. There's only 1 way to finish that task. 4 times 3 times 2 times 1 is what we call 4 factorial. Remember, a number factorial is that number multiplied by all the numbers less than it down to 1. Except I note that a 0 factorial is just defined to be 1. It makes certain formulas work out easier. And also it kind of makes sense. There's only 1 way to put 0 people in a row. Just sort of like throw up your hands and say, I'm done. So what we've got out of this analysis here, we could have generalized that to any number of people. So this is kind of an important thing to just remember in enumeration, that the number of ways to put n items in a row is n factorial. You got to arrange things where order matters, n things to arrange, n factorial. Number of ways to do it. Try another one. How many ways are there to pick 3 out of the 5 letters A, B, C, and D and put them in a row? So notice that I kind of stated that as 2 tasks put together, pick 3 out of the 5, and then put those 3 in a row. But you don't have to think of it that way if you don't want. You can come up with another sequence of tasks that does the equivalent thing. I think probably the easiest thing at this point is to think of it as 3 tasks. Pick your first letter in your row, your second letter in your row, and your third letter in your row. And there would be 5 times 4 times 3 ways to do that for a total of 60 ways. Now, notice, kind of looking ahead to possible formulas for things, 5 times 4 times 3, our answer, could be cleverly written as 5 times 4 times 3 times 2 times 1 divided by the 2 times 1. And so that turns into 5 factorial over 2 factorial. And 2 is kind of interesting because 2 is 5 minus how many people you had to pick to put in the row. So if you think about it, what you've really got here is possibility of a formula. Suppose that you've got n items, okay? And you're going to pick r items out of the n items and order them in some way. So the order in which you pick them is important. It's noted, as the textbook says. Well, the number of ways to do that can be found using this multiplication principle up here, but just generalizing it to the n and the r instead of the 5 and the 3. And so, you know, the number of ways to pick the first item would be n, and then there would be only n minus ways to pick the second item. And by the time you get down to the rth item, that's going to be only n minus r minus 1 things to pick from. And so that product would be your answer. And if you did this little multiplying and dividing trick that I've done down here, then you could actually turn that into this formula, n factorial over n minus r factorial. So that concept is called permutations. One notational way of writing it is the permutations of n things taken r at a time. The book sticks the n on the left and the r in a subscript on the right. Okay. Let's try again. How many ways are there to select a president, a vice president, and a secretary from a club consisting of 10 people? Well, without telling you, they've put you in a situation where order is noted. You know, if you're going to pick, say, president, vice president, and secretary, the first person you pick is the president, the third person is the vice president, third person is the secretary. Order is important. So you're in the permutation situation. So you could say that it's 10 times 9 times 8, or you could whip out the formula and say it's the number of permutations of 10 things taken 3 at a time. And so it is, oops, and that's a mistake there. That should be a 10 minus 3 on the bottom. So it should be a 7 factorial on the bottom. Very sorry, I'll fix that maybe in the notes that you see put up on Canvas or wherever. Okay, let's try exercise 1 out of the textbook. So let's say that you need to make a 3-digit number, maybe on a license plate or something like that. And so you're allowed to use each of the 10 digits, okay? And there's 10 digits, 0 and then 1 through 9 makes 10 digits. And you're allowed to repeat digits. And it's totally okay to have like a 0 at the beginning or something like that, because it's really a sequence of digits, not like an actual number that you're making. Well, there'd be 10 ways to do the first digit, 10 to do the second, and 10 to do the third. So 10 cubed. Great. So a very simple application of the multiplication principle. Here's some example I decided I didn't want to work with. And now, how about exercise 3? So I'm going to have to read this one out of the book because I don't quite remember what it was. And you should go to the book too and take a look at it. So exercise 3 is section 1-2. How many different license plates are possible if a state uses A, 2 letters followed by a 4-digit integer? Leading zeros are permissible and letters and digits can be repeated. That's part A. Let's look at part A. Well, it looks like we got 2 tasks. We got to make our 2 letters, and then we've got to make our 4 digits. Well, 26 squared for the 2 letters, 26 times 26. So kind of multiplication principle within multiplication principle here. And 4 digits, 10 to the 4th, just like in the preceding example. So 26 squared times 10 to the 4th is our answer. And I don't think that you should simplify or compute out these kinds of numbers when you're doing these problems, unless there's like some specific practical reason that you need to do so. Because when you write them like they are, like I've got it highlighted there, everybody can see your thinking that led to your answer. They can see how you were applying the multiplication principle. I still do think it's a good idea to show your thinking, at least to the extent of showing these little tables, with the tops and the bottoms over the lines, your task on the bottom and the number of ways on the top, and little multiplication signs in between. That clarifies your thinking further. But let's look at part B. Says, okay, here, what if the license plate has 3 letters followed by a 3-digit integer? Okay. Well, you can see how to modify the ideas from the previous part, 26 cubed times 10 cubed. So like if somebody want to write that down as an answer, I would say that's enough work shown right there, simply by not computing it out. Let's take a look at exercise 5, okay? How many 4-letter code words are possible using the letters in Iowa? If, part A, the letters may not be repeated. And so if you realize, that's just like putting 4 people in a row. Making a word with letters, put the letters in a row. This is like putting 4 people in a row. 4 factorial, we've done that word. Part B, the letters may be repeated. 4 letters, 4 tasks. First one, second one, third one, fourth one. 4 times 4 times 4 times 4, 4 to the 4th. Great. Now, so far we've been working with problems where the order in which you select things out of the big starting set is important. But what if the order of selection is not important? Imagine that you needed to pick 3 letters out of the 5 letters A, B, C, D, and E. Okay? And you just need the 3. Order's not important. And so you start thinking about it, you think, well, I don't even know how to do this where order is important. And in that case, there would be, the 5 times 4 times 3, the 60 ways to do it, like we thought about, permutations of 5 things taken 3 at a time. But it might be useful just this once to laboriously, systematically list out the 60 ways that you can pick the 3 and put them in a row, okay? And so I've got them listed out here. In this first little column here that I'm trying to make, there we go, all the letters are A, B, and C. It's just the order in which they came changed. And here, all the letters were A, B, and D. The order in which they came was different. And if you go down looking through this list, you'll see that in each of the little groups, the letters are the same. The order in which they were arranged was the only thing that differed. And you'll notice that each group has 6 items in it. And that's because there's 3 factorial, which is 6, ways to put 3 things in a row, okay? So 60 is like way too big. It's way too big to be the correct answer. But 60 comes in 10 groups of 6. And it's actually the 10 groups that's the interesting thing, because that means there's 10 little subsets of letters of size 3. The 10 is the correct answer. We can get to the correct answer by taking the answer that's too much and dividing by the size of the groups that the too much answer could be arranged in. So this is a great way to kind of correct an initially wrong answer in the subject of enumeration, is if your wrong answer comes in groups, correct by dividing out by the group size. Of course, all the groups have to be the same size for that to work. So this concept, the number of ways to pick 3 items from 5 items when order is not important, that's pretty common thing, and so we give a name to it. In general, we call it the number of combinations of n things taken r at a time. So it's like the number of permutations, except order is not important, and the way you get it is you take the permutations, which is wrong, but divide by the r factorial, the group size, the number of ways to arrange the r things that you've picked. And so if you play with the math a bit, here's the permutation formula, n factorial over n minus r factorial. We're dividing by r factorial, and let's just go ahead and put everything on one denominator, and you get n factorial over r factorial times n minus r factorial. That's another important formula you should memorize. And here, by the way, is a little notation for that quantity. It's one set of parentheses, n on the top, r on the bottom, no fraction line or anything like that, because it's not a fraction. And that just stands for the number of combinations of n things taken r at a time. It's often called n choose r, for quick and short, n choose r. So quickie example here. Say a set has 100 elements. How many subsets of size 12 does it have? All you need to realize is that a subset of size 12 is you picking 12 items out of the 100 items, order not important, because in a set, the things you list out in the set, it doesn't matter what order you listed them out in. So the answer is 100 choose 12, kaboom, right away. So just go ahead and you could write this if you like, or you could just be coy and write the 100 to 12 in the parentheses. Another example, say that a class consists of 12 men and 15 women, and you have to make a committee that represents the class. And there's some rules for the committee. It has to consist of 2 men and 3 women. In how many ways, sometimes you get tired of writing a lot of stuff, can this be done? Well, the job of making the committee can be broken down into 2 tasks. Pick your men, pick your women. Okay. Now, those tasks could actually come in either order, and you still get your committee. But I need to pick an order to start working the problem. I think I can use a multiplication principle here, because the number of ways to perform my second task, picking the women, is the same no matter how I choose to pick my men. So multiplication principle is at hand. How many ways to pick the men? Well, there's 12 men. Got to pick 2 of them. 12 choose 2. How many ways to pick the women? There's 15 women. Got to pick 3 of them. 15 choose 3. And so there we are with our answer. Best not to simplify unless you have to for some practical reason. Number 9 is a fun one. Here, let me take a little sip of coffee. And let's read it out. Find my place again. Sorry. Okay, number 9. So the World Series in baseball continues until either the American League team or the National League team wins 4 games. How many different orders are possible if the series goes 4 games, 5 games, 6 games, 7 games? Now, by orders, I mean like how many ways are there to state, who wins each game in the series? And so we need like a code for this. So like imagine the series went 7 games, okay? Like this might be a way it came out, where the American League team won, then the National League team won twice in a row, but then the American League team came back and won the final 3, and so they've won 4 games. The series ends at 7 games. Or maybe it could come out this way, where National wins, then the American League team comes roaring back and wins 3 in a row, but the National League wins that last game. So that's 2 of the presumably several other ways that a 7-game series could have gone. Okay, so we're looking at part A, where the series goes 4 games. How many ways are there to do it? Now, I know you could list this out very easily, but I want to kind of think about a systematic way to think about it to help us out, with more games, which is what they're going to ask about next. So to sticking with this, 4 games. There's actually 2 cases to consider here. One case is that the American League wins the series. The other case is that the National League wins the series. And what we'll do is we'll figure out how many ways in each case and add them together, and that'll be our answer for part A. So in the case where A wins the series, let's just write down like these lines that represent the tasks of like figuring out who won each game. That last line has got to have an A over it, right? They've got to win the last game because they win the series. And there's no way that a series ends with the person who did not win the series losing the last game. That's just how series work. So there's got to be an A there. It is the World Series where you got to win 4 games to win the series. Well, that means that all 3 of these choices here also have to be A's. So there's really only one way, A, one way. And so you can think that's a really stupid long way of thinking about it, but give me a moment. Okay, case 2. What if the National League wins the series? Well, that's also going to be just one way. And I don't have to like write out an analysis like this because there's a symmetry, between the A and the N. In the second case, I'm just reversing the roles of the A and the N. So I know the analysis will end up with an answer of 1, just like case 1 did. This got cut off on the bottom there, but in part A, the answer is 2. There's 2 possible World Series ways of things happening when it goes 4 games. What about 5 games? This is part B of the problem. How many series are possible? Again, we'll do two cases. But now that we realize that both cases, A wins and N wins, are going to yield the same number of ways, we're just going to suppose that A wins and we'll double our answer. Okay, so we put A here at the last of the 5 games, and we think about those first 4 games. 3 of those 4 games have to be where A wins, so that A will have 4 victories winning the series. So we got 4 spots there. We just gotta pick 3 of the 4 spots to have an A in them, okay? So that's taken 4 things and picking 3 of them to have the A's in them. So it's the number of ways to pick 3 things out of 4 things, which happens to be 4, but I'm just going to leave it unsimplified. So our answer there is 2 times 4 choose 3. Part C, what if the series goes 6 games? Well, again, we're going to double what happens where A wins the series. And A has to be the victor in the last one. So we're focusing on the 5 games that come in front. 3 of those 5 needs to be A's. Same analysis says 5 choose 3 is how many ways to fill in 3 of the 5 spots with A's, and the other 2 are N's. So again, 2 times 5 choose 3. And you can see if the series goes 7 games, then it's going to be 2 times 6 choose 3. So actually, the number of total possible World Series outcomes of all game lengths, 4, 5, 6, or 7, is going to be twice the 3 choose 3. That's the one way, where all 3 of the previous games had to be, the winner winning. 4 choose 3, that's the case where there were 5 games. 5 choose 3, where there were 6 games. And 6 choose 3, where there were 7 games, doubling. And that would be our answer. So, in real life, a problem like this might come to you as how many World Series are possible? And you would have to break the analysis up into these cases, 4 games, 5 games, 6 games, 7 games. And the subcases, A wins, N wins, to get to the point where you can use the multiplication principle and your permutation and combination formulas. And when you do those cases, it's really going to be really important as a problem-solving principle, not to just write out the answer for an easy case, but to analyze the easy case in some way that can be generalized to, the more complex type of cases. Good problem-solving technique. Let's head for another example. How many ways are there to seat 5 people around a table? So say you got people A, B, C, D, and E, okay? So you could put them like this. A goes in this chair, and then, B goes in this chair, and so on, clockwise. Now, that I'm going to count as the same seating arrangement as this one here. Notice that this one here, everybody has just been rotated 1 seat over to their left, okay? So it counts the same seating arrangement because everyone has the same experience of everyone else around the table. It's the same people to their immediate left and right as in the other arrangement. The same people diagonally across and all that kind of stuff. So rotations of one arrangement count as the same arrangement for us. And so we got to count the number of truly different arrangements. So how can we do this? We could start off, say, hey, we got to put 5 people into the 5 chairs, okay? Like this might be, so this might be like one way. But that's too big an answer. It counts the different rotations as different, and we need to count them as the same. But what you notice is that for any one placement, there are 5 rotations, of which that one is one of them. Here's one rotation, but you could have also moved everybody 2 over, or 3 over, or 4 over. or 5 over. So you have to divide by the 5 ways that you could rotate around. And the answer ends up being 4 factorial. 5 factorial divided by 5 would be the 4 times 2 times 2 times 1, 4 factorial. So nice thing to remember. You have n people, you need to put them around a table. How many arrangements? N minus 1 factorial. Let's complexify the problem a little bit. And you should do this when you're working through the textbook, working through example problems, working odd number problems and looking in the back of the book, just practicing. Try complexifying the problem for yourself. How many ways are there to seat our people, A, B, C, D, and E, if A and B are fighting and they will not be seated next to each other? So here's one way to think about it. Think about an easier version of the problem, which is clearly no restrictions, no fighting. In that case, there would be 4 factorial ways, just like we analyzed it before. But that's too many ways. It includes the ways where A and B are next to each other. So what I'm going to do next is figure out, okay, well, how many ways are there to do it wrong, to put people around the table with A and B next to each other? What I can do, this is kind of clever, is I can treat A and B as a little joined unit, okay? So like B is to A's left, and they're just joined like at the hip, okay? And then I've got C, D, and E, and so I've got 4 items, and I got to sit them around a table. That would be 3 factorial ways. And so that would be a lot of the ways to get them to the table the wrong way with A and B together. But not all the ways, because in this way, B is to A's left, but it's also possible that they could have been joined where B was to A's right, But again, that's 3 factorial ways. So the total number of wrong ways is 2 times 3 factorial, and that needs to be subtracted out of the total number of no restriction ways, okay? So this is a way that you'll often choose to solve enumeration problems when they're too hard. Look at the easy way with no restrictions and then subtract off the wrong ways where you violate the restrictions. In a way, you can think of that as an application of that inclusion-exclusion principle that we were looking at in the previous section. The original thing is too much, corrected by subtracting off. Hey, back in high school, you learned about the binomial theorem, okay? Which was this great formula for multiplying out, raising binomials to high powers. So like say you got a binomial, 2 terms, nomos in Greek, term, x plus y, that's a binomial, 2 terms, x and y. And you raise to the 0 power. Well, that's a 1, okay? How about x plus y to the 1st power? Well, that's x plus y, but let me kind of stupidly write it as 1x plus 1y. How about x plus y squared? And you kind of like FOIL it out, which depends on using the distributive property a couple of times. And you get x squared plus 2xy plus y squared, which I will stupidly write as 1x squared plus 2xy plus 1y squared, okay? And similarly, x plus y cubed. If you just like did all the work laboriously, you would get x cubed plus 3x squared y plus 3xy squared plus y cubed, which I write that way with the 1 sitting where they don't really need to be. I'm going to do a little bit more detail, though, on just like thinking, like let's kind of think here, like how would you do all that multiplication out? And one way to look at it is, hey, any term in the multiplication means choosing something from the first factor, like maybe I choose the x, and then something from the second factor, like I choose a y, and something from the third factor, like maybe I choose this x. And so I've chosen 2 x's and a y. X squared times y is what would get multiplied together. So that would be one of several ways to get an x squared y. And how many ways are there to get 2 x's and a y? Well, it would be the number of ways to choose out of these three things, two of them to pick an X from. The other one gets a Y. 3 choose 2. 3 choose 2. And if you follow through the math on 3 choose 2, the 3 factorial over 2 factorial, 1 factorial, it works out to 3, which just like happens to be this thing right here. And that actually works for all these other factors. They're all combinations. In fact, in general, it works like this. A plus b to the nth is always just, well, 1 a to the n. So this is like where you said, all right, I'm going to pick an a every time. I'm never, ever going to pick a b. So it's the number of ways to pick no factors out of my n factors to get a b from, 1. And then how about the next up comes n times a to the n minus 1 times b, okay? To get these a to the n minus 1 b's, out of those n a plus b factors, I picked one of them to have a b, and the rest are going to have a's to pick from. And there's n choose 1 ways to do that, which works out to n. And so on and so on. N choose 2 for 2 b's, all the way up to n choose n minus 1 for the n minus 1 b's in the next to the last term. And then b to the n, there's a 1 in front because there's one way to choose all n to pick a b from. So that could be proved more rigorously with mathematical induction. You might have done it if you took discrete math. But I think this is a pretty convincing argument right here for the binomial theorem. Related to the binomial theorem is Pascal's triangle. And so like here I have written out the coefficients for the various expansions. But I've gone a little further. I've gone up to like an x plus y to the 7th power. And I'm sorry, I kind of cut my work off there at on the 7th row. So the first row was just a 1. The second row was a 1x and a 1y, and then a 1x squared, a 2xy, and a 1y squared, and so on. And the last row should have been a 1 that you can't see, and then a 7, 21, 35, 35, 21, 7, 1. And you could go on like that, writing rows and rows forever. And you get what's called Pascal's triangle. But it's a kind of an interesting when you look at Pascal's triangle, there's all kinds of cool patterns. One cool pattern is that when you add up each row, it doubles every time you go down. So like row 0 here, I call it row 0 because it comes from x plus y to the 0th power. That's a 1. Row 1 adds up to 1 plus 1 is 2. That's twice as much as before. Row 2 adds up to 4, which is twice as much as before. In fact, every row, like here's row 4, that one adds up to 16, which is 2 to the 4th power. So the rows double as you go down, and the formula for like the nth row is 2 to the n. Another cool pattern. Say you just start with one of the 1s on the end, and you decide, I'm going to go along a diagonal and add up what I get. So a 1, and then I'll go down here diagonally to the 2, and then I'll go down diagonally to the 3. I'm going to add those 3 together. 1, 2, and 3 make 6. And lo and behold, if I like pivot and switch down the other way, I come to this 6. Try a 1, 2, 3, 4. That adds up to 10. And pivot the other way and go down, and you get the 10. All kinds of cool patterns in the binomial, in the Pascal's triangle. But the coolest, and well, there's actually 2 that are the coolest and the most useful. One is a kind of a symmetry. Every row is symmetric. And that leads you to an insight about the binomial, about the combinations coefficients, because the Pascal's triangle is just those combination coefficients. The insight is that n choose r has to be n choose n minus r. always, because of the symmetry of these rows. But another way of thinking about it is, the number of ways to choose R things out of N things. Well, though I could choose a set of R things out of N things by choosing which N minus R things to reject. You get the idea? And so I could count how many ways to reject N minus R things. And it's got to come out as the same as the number of ways to accept R things. Another cool thing that a lot of people notice about Pascal's triangle is to get any one of the numbers on the triangle, like the 6 here, all you got to do is to go up to the previous row and add the number to the left above and the number to the right above, and you get it. It works all the time. Like 4, it's a 1 and a 3. Even the 1s work. If you think of there being like zeros on the outside, this 1 would then be like this 0 and this 1. And that works out to this formula. And the book actually asks you to prove it more mathematically than, not just like talking about Pascal's triangle, but actually to prove it mathematically. It's an exercise. Oh, let's see, another little interesting problem. How many ways are there to spell a word with the letters of Mississippi? Now, this is a lot harder than how many ways to spell a word with the letters of Iowa, I-O-W-A. Because in that case, all 4 letters, I, O, W, and A, were different. But here, the letters of Mississippi, there's like 4 I's that are the same, and there are 4 S's that are the same, and there are 2 P's that are the same. So how do we solve this problem? We can't just say that it's going to be 11 factorial, just 11 letters there. So, well, the way to solve the problem is to blindly go ahead and do what you know you can't do. Assume at first that all letters are different, okay? So maybe we could write the Mississippi as M, I1, S1, S2, I2, S3, S4, I3, P1, P2, I4. So the subscripts make the letters different. Then there would be 11 factorial ways. But those ways come in groups that really should count as the same. Because there are 4 I's that really should count as the same. Those I1, I2, I3, I4, in any spelling, they could have been arranged in those I places where they've been stuck, but they could have been rearranged within those four places in 4 factorial ways. So we got to correct for that. We'll divide by 4 factorial. And similarly, we got to correct for the fact that the 4 S's that are written different, S1, S2, S3, S4, really are the same. And to correct for that, consider how many ways are there to rearrange the S1, S2, S3, S4 amongst the places that you picked for the S's. And so we're dividing out by another 4 factorial. And similarly, correct for the 2 P's, 2 factorial. And if you feel like it, for fun, correct for the 1M, 1 factorial, makes no difference at all. But that does lead you to a nice general formula. If you've got a word made up of N total letters, but there are S different actual letters used, and the first letter is repeated in 1 times, and the second letter in 2 times, and the S letter in S times, then the general way of doing it is N1 factorial over that product. Okay, so that's it on section 1.2, all done in one screencast. Hope you enjoyed it. See you soon.